very much. It's a real pleasure to be here. So thanks for the invitation to speak. And since the workshop is about high-dimensional phenomena, when I was invited to speak, I asked the organizer if they considered 2 to be a high dimension, and they said yes. So my conscience is clean. So let's start from the Brunn-Minkowski inequality. So given 2 subsets of Euclidean space, we can construct a new set for some lambda between 0 and 1. The set 1 minus lambda a plus lambda b is just the set of points of the form 1 minus lambda a plus lambda b, where a is in a and b is in b. And then we have the Brunn-Minkowski inequality, which says that for 2 non-empty Borel sets, the volume of this set to the power 1 over n is greater or equal to the corresponding convex combination of the volumes of the individual sets. Now, if we wanted to do the same thing instead of Euclidean space on a manifold, we don't have addition or dilation on a manifold, but we can make sense of this operation if we know that this set is actually the set of all points which lie on segments joining the set A to the set B and dividing those segments by a ratio to lambda of lambda to 1 minus lambda. So for instance, if lambda is 1/2, it's just, this set is actually the set of midpoints of segments joining the 2 sets. And this notion actually makes sense on a Riemannian manifold, where we have geodesics. So given 2 subsets of a Riemannian manifold and some lambda between 0 and 1, we can construct a new set by taking points of the form gamma of lambda, where lambda is a minimizing geodesic, which visits the set A at time 0 and the set B at time 1. And, so for instance, if lambda is 1/2, we just take midpoints of minimizing geodesics. So these are length minimizing curves on the manifold, and this we can construct a new set in this way. On a manifold, there may be more than one such geodesic joining each pair of points, but we take all of them, and this is our new set. And then, in fact, there is a Riemannian version of the Brunn-Minkowski inequality. So in its functional version, the Borel-Braskin-Philipp inequality was proved by Cordera, Erskine, McCann, and Schmuckenschlager in 2001, and this formulation appears in a paper by Sturm from 2006. If you have a complete Riemannian manifold whose Ricci curvature is non-negative, and so actually you have the Brunn-Minkowski inequality again with the Lebesgue measure replaced by the Riemannian volume form. And in fact, this is even an equivalence. So if you knew this inequality for every pair of sets and every lambda, you could actually deduce that the Ricci curvature of the manifold is non-negative. So, so this condition is necessary. So let's take a look at what happens, how things break down on the hyperbolic plane where the curvature is -1. So let's consider 2 points on the hyperbolic plane. Let's take A to be a ball of radius 1 centered at P, and B to be a ball of radius 1 centered at Q. And then, this is the upper half plane. These, for now, are the sets A and B, these 2 circles, disks. And in between, ignore this mesh, it's just a solid shape, is the set consisting of all midpoints of hyperbolic geodesics joining A to B. So this is lambda equal to 1/2. If you take lambda equal to 1/2, then this is the set we get. And now what we're going to do is we're going to take these disks further and further apart. So they still have radius 1, even though they appear smaller to us, but that's just because of the model. So these disks are always radius 1. And as you can see, the area of the set of midpoints is becoming smaller and smaller, and actually goes to 0 as we take the distance to infinity. So the right-hand side of the Brunn-Minkowski inequality is constant, but the left-hand side tends to 0, so it shows you that there is no Brunn-Minkowski inequality on the hyperbolic plane. Brunn-Minkowski combines volume and Minkowski summation. So one thing you can do is change the Riemannian volume form into some other volume form, and then you get a very rich theory which concerns properties of measures, curvature dimension of measures, and so on and so forth. And we are going to actually focus on the other element, which is the Minkowski summation. We're going to change what a Minkowski average or sum is and see how this affects Brunn-Minkowski. And in particular, we're going to start by trying to fix the situation on the hyperbolic plane where Brunn-Minkowski broke down by changing the way we take averages. So Hor cycles were conveniently introduced yesterday by Professor Hug, so I'm going to just recall what they are. So in this picture, we can see the disk model and the upper half plane model, and the circles which are perpendicular to the boundary are geodesics. On the upper half plane, there are also those vertical geodesics. And the circles which are tangent to the boundary, those are Hor cycles. And in the upper half plane, it's also those vertical lines, they're also Hor cycles. So, for instance, there are limits of circles as we fix a point on the circle and take the center to infinity, to a particular point at infinity, and then the limit is a Hor cycle. And we are going to consider Hor cycles actually as parametrized curved. So we're going to fix an orientation of the hyperbolic plane, and we're going to consider constant speed oriented Hor cycles. So they're parametrized by constant speed with respect to the hyperbolic metric, and also we don't reverse them in both directions. There is a preferred direction for each Hor cycle. So for instance, if you're working in the disk, you can take counterclockwise constant speed circles tangent to the boundary, or in the upper half plane, the same, as well as constant speed horizontal lines in the positive direction. And constant speed, again, is with respect to the hyperbolic metric. And once we've fixed this parameterization, then actually through every pair of points on the hyperbolic plane, there's a unique unit speed oriented Hor cycle. And through every tangent vector in the tangent bundle of the hyperbolic plane, there's a unique constant speed oriented Hor cycle. So the situation is similar to the situation with geodesics. So just notice that, for instance, if I take these 2 points, this point here and this point here, I don't know if it's clear, but there's actually, so if the lower one is x and this one is y, you can, if you want to go from x to y by a Hor cycle, you go through this one, and if you want to come back, you go by this one, because you have to always go counterclockwise, and you can't pass through this point in infinity because it's not in the hyperbolic plane. So the Hor cycle from x to y is different from the Hor cycle from y to x. But anyway, we still have the situation, and we can define the whole cyclic Minkowski average of two sets. We just repeat the same definition, but replacing the word geodesic by the word Hor cycle. So we take the union of Hor cycles starting at A, ending at B, evaluated at lambda. So here's an example. So these are the same identical disks from before, and up here is the green set is what is the usual geodesic Minkowski average of these 2 points. The horocyclic average is actually down here. So since vertical lines from A to B are one example of Hor cycles, then it's easy to see that this horocyclic average is actually going to contain a third disk of the same radius as A and B. So in particular, this the area of this set is going to be actually strictly larger than the area of each individual disk, and this kind of suggests that now with this new operation, actually Brunn-Minkowski is going to hold. And this is in fact the case. So for two Borel non-empty subsets of the hyperbolic plane, the area of this horocyclic Minkowski average to the power 1/2 is indeed greater than the corresponding convex combination of the areas of A and B, the bar 1/2. As for equality, we haven't completely characterized the equality cases, but when A and B are concentric disks, or if one of them is a singleton, then there is equality. The previous image shows you that just two identical disks is not an equality case. Okay, is this part of a more general phenomenon? So we managed to fix the situation in the hyperbolic plane by adding curvature to the curves we are using to interpolate. So does it mean that if there is negative curvature in our surface, we can somehow use the curvature of the interpolating curve to somehow cancel its effect? So we're going to discuss Minkowski summation with respect to more general families of curves on surfaces. And I forgot to mention that there's also a holocyclic Brunn-Minkowski inequality and or more generally Borel-Braskamp-Leib inequality, which is just a functional version. Okay, so what is a spray? If you have a smooth manifold, a spray on the manifold is a vector field on a tangent bundle, satisfying two conditions. One is the semi-spray condition, and one is the homogeneity condition. Now, forget about this. I will explain to you what these conditions mean. If you have a curve on the manifold, you can lift this curve to the tangent bundle by just looking at the tangent of the curve. So the tangent of the curve is a curve of the tangent bundle. So there's a natural lift. So the semi-spray condition means that the integral curves of the spray are all lifts of curves on the manifold. So each integral curve of gamma comes from a curve on M. And the homogeneity condition means that the spray is fiber-wise too homogeneous. So if you wrote it in coordinate and the function describing the spray would be too homogeneous with respect to the direction coordinates.
Just to make sure I'm following, so both geodesics and horocycles are special cases?
Yeah. So if you take those integral curves of gamma, which are lifts of curves on the manifold, and project them back, and you look at the original curves, this is what we call gamma geodesics. And the homogeneity condition means that if you have a gamma geodesic and you reparameterize it by a positive constant, you'll get another gamma geodesic. So this is the situation with geodesics. It means that we don't want different curves starting from the same point in the same direction. If you go in the same direction, in a different speed, you end up traversing the same curve just at a different speed. So, for example, the geodesic spray of Riemannian manifold. So on the tangent bundle, we have the geodesic flow. It's induced by the geodesic spray. So geodesics are gamma geodesics of this spray. The horocycles we discussed earlier are, with the parametrization that we gave them, are geodesics of some spray. And generally, on a surface, on a two-dimensional surface, you can write an ODE describing a second-order ODE describing a spray, and you have a natural, for a curve on a surface, you have a natural frame, like a finite frame. You have the tangent and the normal. So using this frame, you can express the second derivative, the covariant derivative of the curve, and it boils down to just specifying one homogeneous functions, sigma and kappa. It's the same as specifying a spray on a surface, on a two-dimensional manifold. And this kappa is called kappa because it's, well, up to homogeneity, it's the geodesic curvature of the curve.
Could you remind, so which sigma and kappa correspond to geodesics and to horocycles?
So, okay, so if both of them are 0, it's geodesics. And if for horocycles this is 0 and kappa is exactly just the norm of gamma. So the silliest one homogeneous function, just the norm of of gamma. So if you take, yeah.
That Hall cycles can exist on any manifold, not just hyperbolic, right?
Okay, what does exist on any manifold is curves of geodesic curvature 1. So Hall cycles are curves of geodesic curvature 1, so if you're on a manifold, you can always have acceleration which is exactly of norm 1, and if you're on a surface, okay?
So on the normal space, it would be like a circle. In a random circle.
Yeah, exactly. So now if you have a spray, you can do exactly the same thing. You can define a set. Given two sets, you can define a new set, which is just a collection of points of the form gamma of lambda, where gamma is a gamma geodesic starting at A and arriving at B at time 1. So if gamma is just the trivial spray in Rn, this is just usual Minkowski average. For the geodesic spray and Riemannian manifold, you get the geodesic Minkowski sum that we defined in the beginning, up to this remark that in this definition we don't require there's no, for geodesic there's a notion of a minimizing geodesic. So you don't take just any geodesic, you take minimizing geodesic. So if you take all the geodesics, it could be a bit silly because some geodesics can keep just going and stop minimizing, and so it can create potentially a very large set, but we'll deal with mostly the case where all the geodesics are minimizing and we don't have this problem. So, yeah, there's also a spray on the hyperbolic plane that gives us 4 cycles. So, if you have, the theorem says the following thing: if you have an oriented Riemannian surface, and gamma is some simple proper, I'll elaborate on these two conditions soon. Metric spray. So metric means that the curves all are parametrized by constant speed. As in the case of geodesics and as in the case of Hall cycles, the speed of the curves in your family is always constant with respect to the underlying metric. So this means that you don't have the sigma term that we had before. The acceleration is always perpendicular to the velocity. So you have the metric implies that the spray is determined by. By the way, I haven't said what this perp means. It means rotation by 90 degrees in some fixed direction, but since the surface is oriented, then we have some rotation by 90 degrees in some positive direction. And so now we have this function kappa, which is associated to every metric spray. And then the following are equivalent. On the one hand, you have Brunn-Minkowski for your spray. And 2, the spray is magnetic, meaning that the function kappa is only depending on position. So the kappa of a vector is the norm of the vectors times some function on the manifold. So it's independent of the direction of the curve, just on its position. And you have this formula, where K is the Gauss curvature of G. So kappa equals 0 corresponds to geodesics, and then you recover the condition that Brunn-Minkowski is equivalent to non-negative curvature, in this case Gauss curvature. The case of Hall cycles is the case of kappa identically equal to 1, and then K is -1, kappa is 1, and this is 0. So you get, again, that this condition is satisfied. Okay, so regarding these two conditions, these are topological conditions. So simple means, it means that the exponential map of the spray is a diffeomorphism, or it means that when you fix a point and you just look at all the gamma geodesics from that point, they don't intersect each other, they foliate the manifold nicely. It creates some homomorphism or C1 diffeomorphism from the tangent space to the manifold. So in particular, the manifold is diffeomorphic to R2. So this theorem is for simply connected surfaces. And proper means that the gamma convex hull of a compact set is compact. So you have a family of curves, you can take a convex hull with respect to this family. You just take the smallest family that contains the curve through every pair of points in the family. There is some convex hull. You want the convex hull of compact sets to be compact, and there are some sprays that don't satisfy that. Weird sprays don't satisfy that. So under these two conditions, we have this theorem. Moreover, you can replace the Riemannian volume form by some other volume form. So you take the Riemannian volume form and multiply it by some density, and then the following are equivalent. Brunn-Minkowski with respect to this new volume. And 2, the spray gamma is magnetic. So again, this kappa depends only on position, but not with respect to the metric G, but with respect to some other metric which is conformal to G, this metric. So this is one condition, and the other condition is that this inequality is satisfied. So this time it's a quantity not on the manifold but on the tangent bundle. This is sort of a Hessian. So if you think, if in the geodesic case, this is the Hessian of phi.
Do you need phi to be convex here? Or no?
No.
But if kappa is equal to 0, does this have some implication on phi?
Yeah, so for instance, if kappa is equal to 0, you know that for geodesics, you can't get Brunn-Minkowski with the exponent 1/2 unless phi is constant.
Okay.
So for instance, if kappa is 0, then phi has to be yeah. Okay, you can't see it in this formula, but you can see it in the formula that it has to be magnetic with respect to the conformal.
Okay.
I'm not sure if it's answered.
Sorry?
Did it answer your question?
Yes, yes.
Okay. And this E2 here is some canonical vector field on the tangent bundle. You have, on the tangent bundle of a Riemannian surface, you have two canonical vector fields. You have E1, which is the geodesic spray, and E2 is another just natural vector field on the tangent bundle. And so this condition is some condition which has to hold on the tangent bundle. So in particular, if you take kappa equal to 0, this is the weighted generalized Ricci, or in this case Gauss tensor of the weighted Riemannian manifold Mg with this volume form. And finally, what if you wanted the Brunn-Minkowski with exponent 1/n? In this case, the theorem I have is with magnetic here. So I think that there's a saying that if you can't prove a theorem, you need to gradually move things from the conclusions to the hypothesis. So I moved the magnetic from the hypothesis to the conclusion of the hypothesis. Now we have this theorem. That if you have a simple proper magnetic metric spray with some volume form and some n, now different from 2, then Brunn-Minkowski is equivalent to non-negativity of this quantity on the tangent bundle. So I think I finished early. I probably went very fast, so I hope maybe you have questions, but that's all I had to say, so thank you very much.